Welcome to Introductory Chemistry with Dr. H. This is a video about molarity. First, I'm going to talk about what molarity is, and then how it relates to concepts we already know, like moles and mass and the number of particles. And then I'm going to talk about how one understands changes to molarity when you dilute a solution. We're talking about solution chemistry here, and what molarity is, it's the number of moles of a solute, something dissolved in a solution, divided by the volume of that solution. We usually signify molarity with a capital M, and that again is the moles of a solute divided by the liters of solution. So the unit of volume is important here. We usually use liters of solution when we're calculating molarity. Our shorthand notation for moles is a lowercase n. So if we want to do a shorthand notation for molarity, we could write lowercase n divided by V. And importantly, V is the volume in liters. Let's do a quick example of how we might use how we might calculate molarity of a solution. So say we had 3.26 grams of sodium chloride dissolved in a 25 milliliter solution. Let's think about what the molarity of that solution is. So in order to do this calculation, we need to know the moles of the solute, which is sodium chloride. And so for that, we know we need to use the molecular weight of sodium chloride. So let's go ahead and do this calculation. We have 3.26 grams of NaCl, and there are 58.44 grams of NaCl for 1 mole of NaCl. So this will give us our moles. So let me just calculate that. 3.26 divided by 58.44. And so what I get here is 5.57. I'll write one more sig fig. 8 times 10 to the minus 2 moles NaCl. And we know we have 3 sig figs, so I'm just going to go ahead and indicate that to keep track of sig figs as we go along. And now we also know that we have 25 milliliters of solution. So really quick, 25 milliliters. And so for every 1 liter, there are 1,000 milliliters. So 25 divided by 1,000 is 2.50 times 10 to the minus 2 liters, and we have 3 sig figs again. So now it comes time to go ahead and calculate our molarity. We have the things that we need. So the molarity of this solution in sodium chloride is equal to the number of moles, 5.578 times 10 to the minus 2 moles of NaCl divided by 2.50 times 10 to the minus 2 liters of that solution. So let's go ahead and do that math. So 5.57 times 10 to the minus 2 divided by 2.5 times 10 to the minus 2. So the molarity that I get from that calculation is 2.231. We have 3 sig figs, so that's going to be our last significant digit, moles per liter. Okay? And you could also write that moles per liter as a capital M. Importantly, it's got to be a capital M. So the unit could be molarity, or the unit could be moles per liter. Okay, so there's an example of how we calculate molarity and what it is. Let's talk about how this concept of molarity connects to other things that we've already talked about. Moles is the central unit in chemistry, and so we always think about how we connect something that we know at the microscopic level to the number of moles, sort of a macroscopic quantity that we can handle of some substance. So we know that we can connect grams and moles. We already demonstrated that in this video. If we have the number of moles and we want to know the grams of stuff we have, we multiply the number of moles times the molecular mass. And I've indicated here molecular mass because we've got several capital M's floating around here. That's the molar mass of whatever it is. If we have the number of grams, we can divide the number of grams by the molecular mass to get back to the moles. So that's how we connect mass to moles. We also know we can connect moles to the number of particles, right? By multiplying by Avogadro's number. If we know the number of moles, we multiply by Avogadro's number to get to the number of particles. If we know the number of particles, usually we don't know the number of particles, we have to calculate it, but if we know the number of particles, we can divide that number of particles by Avogadro's number to get back to the number of moles. Now we have yet a new connection to this unit moles, which is the molarity. So if we know the number of moles and we have the volume, we can divide the number of moles by the volume to get to this new thing called molarity. Again, molarity is usually used for solutions of things. If we know the molarity of a solution and we know its volume, then we can calculate the number of moles. So one strategy when you're dealing with most chemistry problems, if you don't know where to go to figure out what you need, figure out how to get back to moles, because you can go from moles to any of the other units. Let's do a couple of quick examples to see how this works. So if we wanted to know how many grams of glucose are in a 128 milliliter solution of 0.638 molar glucose, let's look at what we have here. We have a molarity of something. We also have a volume of something. So we can get from molarity and volume, that puts us here, right? We have a molarity and we have a volume. We can use that fact to get back to moles, and then we can go from moles to mass, and we're given the molecular weight to make it a bit easier for us. So we could of course calculate the molecular weight if we knew the chemical formula. So let's go ahead and do this calculation. So let's make this move first. Let's multiply the volume, and importantly the volume has to be in liters, so I'm going to start with 128 milliliters, and for every 1,000 milliliters there is 1 liter. So this will allow me to know the volume of the thing that we have, and we need to multiply the volume in liters by the molarity, which is 0.638 moles of glucose divided by 1 liter. And so notice the units all here cancel, so I'll just sort of show you. The milliliters cancel with the milliliters, the liters cancel with the liters, and we're left over with moles. And I'm not going to write the word glucose because we're just dealing with glucose here. So I'm going to take 128 divided by 1,000 times 0.638. And so what I get in terms of the number of moles is 8.166. We have 3 sig figs here, times 10 to the minus 2 moles of glucose in that solution. So now that I'm at moles, right, I've moved this arrow. I can move now to mass, because the question is how many grams of glucose are there. So now I'm going to do that calculation. 8.166, oops, I put the significant digit in the wrong place, times 10 to the minus 2 moles of glucose. And now I'm going to use its molecular weight. We have 180.2 grams of glucose for every mole of glucose. So I take that number and I multiply by 180.2. And I find that in that solution there are 14.7 grams of glucose. All right, so that's a demonstration of how we can move from a molarity and a volume all the way over here to grams, right? So you can do these calculations all in one sweep, but for now maybe think about doing one segment of this calculation at a time. If you have to move from here to here, do this calculation first and then do the next calculation. You can see that we could have just taken this and plugged it right in there and done one continuous calculation, but maybe at the beginning we break it up into 2 just to make sure that it's clear in our head. Once it's totally clear, of course, then you can just go for it and calculate it all at once. Okay, here's another example. This is a contrived academic example because rarely do you know the number of particles of something because there are just far too many particles for us to conceive of. But here we go. Let's do this sort of academic problem. If you had 2.57 times 10 to the 21st molecules of glucose that were in a 2.1 liter solution, what is its molarity? So this time we're starting over here. We know the number of particles, so we're going to use Avogadro's number. No, we're not. We're going to use the number of particles divided by Avogadro's number to move this direction to find the number of moles. And then once we know the number of moles, we can get to the molarity because we know the number of moles and we're given a volume of that solution, so we can use that trajectory. So let's go ahead and do that. So if we have 2.57 times 10 to the 21st molecules, and I'm going to not write glucose, but you know that it's there. So what I've done is divide that number of particles by Avogadro's number to get the number of moles. So let's go ahead and do the calculation. 2.57 times 10 to the 21st divided by Avogadro's number, 6.022 EE23. And I get 4.267 times 10 to the minus 3 moles. Okay, so that's the number of moles that we've got. Now that we have the number of moles and we also have the volume, we're just going to calculate the molarity. So the molarity of the solution is going to be 4.267 times 10 to the minus 3 moles and we know the volume, and it's already given in liters, so it's just 2.10 liters of solution divided by 2.1. And so what I find is the molarity is 2.03 moles per liter, or the other unit that would be acceptable is just to write a capital M, molar glucose in that solution. All right, so this is a demonstration of starting over here, working our way back to moles, and then getting back into molarity. So you should be able to navigate from any position in this little scheme here to any other position if you have the appropriate information in a problem. So one thing to do when you're starting a problem is to say, what is it that I have? Where, and basically what you're saying is, can I locate myself in this scheme? And then once I can locate myself in this scheme, I know how to move from one place to another. Okay. Another really important thing to realize is there's a fairly simple way of understanding what happens when you have a solution of known concentration and you add some water to it or add some solvent to it to dilute it. To calculate the new concentration, because of course as you add more solvent, the concentration, the number of moles per liters, is going to go down. The more solvent is there, you're adding more solvent, but you're not increasing the number of moles, so the molarity is going to go down. The one thing that stays the same though in a solution, if you have a beaker of something at a concentration and you add some solvent, what hasn't changed is the number of moles of the stuff that's there. We can symbolize this idea algebraically by saying the molarity of a solution times its volume is equal to the number of moles that are there. Once you've changed the volume to some new volume, still when you multiply that volume times the molarity, it's still going to equal the number of moles. So if you have a solution of a known molarity and a known volume, you know its number of moles, and then you dilute it to a new volume, you know the new volume, you can simply solve for the new molarity. You don't have to know any more information. So let's go ahead and do a quick example of that problem. First of all, where this often comes up is in the lab. We often keep stock solutions, which are concentrated solutions of reagents that we use all the time, but they're stored in a very high concentration, and when you need them, you take just a little bit of that stock solution and dilute it with pure solvent to get the working concentration of that material. Okay, so let's read this question carefully. If 280 milliliters of a 2 molar stock solution of magnesium chloride is diluted to make a 1 liter working solution, what is the concentration in molarity of chloride ions in the solution? Okay, so this is important that we're looking actually for the chloride ions that are in solution. Let's think first about what happens to magnesium chloride when we add it to water. So when we take magnesium chloride and we put it in water, what happens, as you already know, is you make magnesium ions that are +2 ions, but you generate for every magnesium chloride 2 chloride ions. So the molarity of the chloride ions is actually twice as high compared to that of magnesium chloride or that of magnesium. Okay, so we'll just keep that in the back of our heads as we're working this problem. So what we're given is a volume and a concentration, so we'll call that M1 and V1. So, and importantly, we're given the volume in milliliters, so we need to make sure that we put it into liters first. And I'm just going to do that one in my head. 280 milliliters is 0.2800 liters. So let's write this out. We have a 2 molar stock solution initially of magnesium chloride. So this is moles per liter, right? And our volume in this case is 0.2800, and that's the last significant digit there. That's the last significant digit there. Liters of that solution. That's going to be equal to a new solution, which is 1 liter in volume. And what we want is the new molarity. So we're going to say M2, that's what we're after. And we know that we're diluting to 1.00 liters of the new solution. So let's just do that math. 2 times 0.28 is equal to 0.560. Okay, and that's moles of magnesium chloride, so I'll just write it out completely. That's the number of moles of magnesium chloride, and that equals M2 divided by 1.00 liters. Now what I'm going to do is divide through, right, by that volume, and of course by dividing through by 1 it doesn't change this number, but it does change the unit, 560 moles per liter, and importantly it's moles of magnesium chloride per liter of solution. So this is our new concentration of magnesium chloride. Now we need to remember that for every 1 mole of magnesium chloride, there are 2 moles of chloride ions, right? So if what we want is the concentration of chloride ions, we need to go ahead and multiply by that 2. So let's do it. So that answer times 2 is 1.12 moles of chloride ions per liter. So that's the concentration, 1.12 moles per liter of chloride ions. Okay, so we've talked now about how to understand how concentration changes when you dilute a solution using the M1V1 M2V2 formula. We also looked at how it's important to keep track of what it is that we're trying to compute the concentration of. Is it the whole molecule, or is it some ion in that molecule that forms upon dilution? Okay, this is a quick video about molarity. I hope you found it useful.